cost of sea level rise on coastal infrastructure caused by climate change. A number of other things, but that's a lot of the work was. This is an area that's been thought about a lot and addressed somewhat. Most people who've done this will pick a little kind of high-income strip of beach homes in South Carolina, as we're all familiar with. And so not only has Delavane put together a more sophisticated model for studying such things, but she's done it global. Think about that, the whole coastal zone for the whole globe. So with that, no pressure. Take us away.
Here you go, Jim.
Thanks, Delavane.
And obviously she'll talk about this work now.
Thank you all for being here today. I'm really excited to get to share the work that I've been doing, looking broadly at how the impacts of climate change get represented in these models that are used for climate policy analysis. Now, as John mentioned, you may have heard something in the news this year about coastal impacts or the melting of the polar ice sheets, which are shown here in this very sensational magazine cover. Today I'm going to be talking to you about the nature of this threat and some policy options that we have to address it. This is an overview of what I'm going to be covering in the next hour. Now, my dissertation looks at how the uncertain impacts of climate change are represented in integrated assessment models, or IAMs. And these are economic models that combine the climate and the energy system in order to measure the costs and the benefits of reducing carbon dioxide. And we use these models in order to inform climate policy. Now, another way of putting this is my dissertation is all about damage functions. So I want to tell you what damage functions are, why they matter, and why I was motivated to study them. Damage functions are mathematical equations that translate warming from climate change to some cost to society. So when we weigh the costs and the benefits of reducing carbon dioxide, this is how we measure those benefits. So this figure shows a damage function with temperature change along the x-axis and the percent of GDP lost along the y. And you might not think that there's enough here to write an entire dissertation about damage functions. But these simple equations are deceptively powerful. So damage functions try to boil down everything that we know about climate impacts into a single equation. So in my thesis, I look at damage functions in 3 different papers. In the first, I study the key drivers of the US government's social cost of carbon. This is the cost to society of 1 additional ton of carbon dioxide. And so in order to understand their estimate of $37, I analyzed the damage functions that were used. And this is work that I did with colleagues at EPRI, who each looked at different modeling components, such as the socioeconomics or the climate modeling. I looked at the damage functions. And this is the first project that performs a model diagnostic and intercomparison of the social cost of carbon models. And this work is important for practical reasons, to add transparency and to evaluate a policy that's being used today to set US regulation, but also for conceptual reasons, to establish the state of the art of how climate impacts are represented in these integrated assessment models. And this work allowed me to think broadly about modeling climate impacts, which is the focus of the rest of my dissertation. Now, in the second paper, I tried to address many of these limitations of damage functions that I discovered in the first. And specifically, I focus on damage functions of sea level rise. And so, in order to do this, I developed a detailed model of coastal impacts and adaptation that I call CAM. And this model produces new global estimates of what sea level rise might cost the economy. And these costs incurred at increasing amounts of sea level rise can be equated in a damage function. Now, the third paper addresses another weak spot of damage functions, which is related to uncertainty and the potential for climate catastrophes. So if we ignore this type of uncertainty in our integrated assessment models, we may be too optimistic in designing climate policy. So I present a modeling approach to overcome this. And the specific catastrophe that I look at is the collapse of the West Antarctic ice sheet. And these 2 papers are linked because I'm able to use the damage functions that I estimate using CAM in the third paper in order to measure the cost of sea level rise in order to see if the potential threat of the ice sheet collapse changes the optimal mitigation policy. Now today I'm going to be sharing my work on these last two papers, but before I get into my research, I'm going to give you some background on sea level rise. Now, a primary cause of sea level rise is thermal expansion. And this is simply the fact that as a liquid gets warmer, it expands. And so as human-caused climate change is raising the air temperature, much of that heat is being absorbed by the ocean, causing their volume to increase. The second main source comes from land ice that melts. And this can be divided into glaciers and ice sheets. And you can see that there's a major source, potential source of sea level rise that's locked up in the polar ice sheets. And I'll be talking about these later. Now, if you actually read the National Geographic article, you would find out that the scientists think that it would take about 5,000 years for all of this to melt. And so we're talking about the Statue of Liberty with water up to her waist. And this is a lot of sea level rise. But I want to convince you about these timescales that we're talking about. So sea level rise is going to be a gradual process with a lot of natural inertia that limits how quickly we can warm up the oceans, and these ice sheets are not going to disintegrate all at once. So don't get me wrong, 5,000 years is very fast on the geological timescale, but on a human timescale, this is going to allow us time to prepare in advance. So how much sea level rise are we talking about for this century, and what could we do about it? This chart shows the projections for sea level rise in 2100 for the highest and the lowest emission cases that were studied in the recent global assessment. And so for the highest climate change case, sea level rise is projected to be 75 centimeters. And in the lowest climate change case, it's still around 45 centimeters. Now you might think that surely if we were to dramatically reduce emissions and stabilize air temperatures below 1 degree C, that we would be able to put the brakes on sea level rise. But this is not the case. And this is the flip side to the fact that sea level rise will only happen so quickly. So that same natural inertia is going to limit how this process of sea level rise. And so past emissions, have already locked in future sea level rise. And this built-in momentum is known as commitment to sea level rise. Now in the climate policy world, we talk about two types of actions: mitigation and adaptation. Mitigation means reducing greenhouse gases in order to avoid climate change before it happens. Adaptation says we will feel some impacts of climate change, so how can we best cope with them? So if mitigation isn't enough to deal with sea level rise, then we're going to need a combination of both policies. And there's two broad categories of coastal adaptation: to protect or to retreat. Protection consists of many types of coastal armoring, such as seawalls or revetments, and it allows us to maintain our current use of the land. The downside is that there can be some loss of wetlands, coastal erosion, it can prevent people from accessing the shore, and protection always has some residual vulnerability. So it may create a false sense of security and encourage development to continue in some of the wrong places. Now, if instead we choose a planned retreat, then we move people and capital away from the coastlines and allow coastal ecosystems to migrate naturally as the seas rise. Now, whichever of these two options we choose, the good news is that our civilization has a lot of experience in dealing with sea level rise. Just look at the Netherlands, where over half the country is already below sea level. So this question of how do we choose what to do and what might that cost led to my developing the CM model. So in this paper, I addressed the critique that damage functions lack a rigorous quantitative basis, and therefore they aren't reliable. So to do this, I developed a detailed model of coastal impacts and adaptation called CM. Now, coastal impacts have been studied for many years, but previous estimates have been overly aggregate, and if they do account for adaptation, it tends to be with very rough assumptions that are applied at the regional or country level. But adaptation is something that's going to happen at the local level. And they also omit other important local effects, like flooding from storm surge, wetland loss, and the effect of relative sea level rise. So I've developed a model that overcomes many of these limitations in order to study coastal adaptation and the residual damages at the local level with the end goal to inform a global integrated assessment model. And one way that I do this is to produce new damage functions of sea level rise. So I mentioned in my first paper, I studied the 3 models that were used to estimate the US government's social cost of carbon. And each of these 3 models has its own damage function of sea level rise. And you can see that there's wide disparity from the DICE model at the top, which assumes very strong quadratic damages of sea level rise, to the PAGE model in the middle, which has some adaptation that kicks in after about 20 years, down to the FUND model, which you can barely see over the x-axis because of its own optimistic assumptions about adaptation. So if you were designing climate policy, you wouldn't know what to believe. Sea level rise could cost as much as 6% of GDP or nothing. So if this is the current state of the art, I saw a real reason to think carefully and thoughtfully about what sea level rise could cost, starting from the bottom up, so that we could move beyond these damage functions. So in designing CM, I felt it was really important to capture these local decisions and local trade-offs, because that's where coastal adaptation is going to happen. And to do this, I parameterized CM using the DIVA database, which divides the world into over 12,000 coastal segments. Now, the previous studies had about 1 or 2 coastal segments per country. So right from the start, this is a huge step up in terms of the amount of resolution that my model is able to handle. So if you just look at the state of California, for example, it has 133 different segments. I've shown 3 here on the map, but the entire coastline is divided into a series of adjoining segments. And each one of these segments has its own geophysical characteristics related to the size, the topography, so how much land might be lost for different amounts of sea level rise, the distribution of storm surge extremes, and the rate of relative sea level rise, which is the change in the land height relative to the sea due to factors like uplift or subsidence. And this is going to act on top of the global trend. And these last 2 are really important because previous studies have omitted the cost of local flooding from storm surge and also this effect of relative sea level rise. Now within CM, I add key socioeconomic and adaptation cost parameters that I use to be able to evaluate these different adaptation options. And I've listed a few of them here. So by combining this data with the DIVA geophysical characteristics, I'm able to evaluate these different adaptation options. And so each one of the 12,000 coastal segments in the model is able to decide on its own least cost adaptation strategy, to protect, to retreat, or to do nothing. And now we'll talk a bit more about how that decision is made. So as I've mentioned earlier, because sea level rise will unfold relatively slowly and smoothly, it's possible for us to update our adaptation decisions over time. And I incorporate this iterative process into the CM decision-making algorithm. So starting out, I assume that we are able to observe the next 30 years of sea level rise. And this is a reasonable assumption because of the natural inertia that I was telling you about. We might not know exactly what sea level in 2100 will be, but we can make an informed outlook for the next 30 years and plan for that amount. And then based on that amount, we can decide how best to act and make this choice about the least cost adaptation strategy. So each coastal segment will make this decision, and then this process will repeat over time, where adaptation decisions can be updated as we learn more about the amount of sea level rise that we expect in the next 30 years. And when I say least cost adaptation, I mean the sum of the adaptation costs, whether to protect or to retreat, and that's decided with the decision period, and then any residual damages that will be faced on an annual basis. Now, protection consists of the cost to build and maintain a generalized seawall, and this cost is based on a recent review of international coastal adaptation costs. And then I account for differences between countries using a construction cost index. Retreat is going to depend on the number of people and mobile capital assets that need to be relocated further inland. And this is based on observed domestic migration costs. Now, depending on which adaptation strategy we choose, there will be some residual damages that are faced. cost of inundation has two components, land and capital. Now, inundated land reflects the fact that coastal countries are going to lose some of their land endowment to sea level rise. Coastal capital will depend on the type of adaptation that's been pursued. So, one of the advantages of a planned retreat is that immobile capital assets can be efficiently depreciated in advance of sea level rise. Whereas in a reactive retreat, this depreciation doesn't happen and we lose the capital asset at full value. Now, about a third of the coastal segments in my model have wetlands. And wetlands provide important ecosystem services that can be valued in monetary terms based on our willingness to pay for them. So if the rate of sea level rise exceeds the wetland's natural rate of migration, then we will lose some wetlands. And importantly, if we choose to build protection, then these wetlands are physically prevented from migrating, and we lose them outright. And finally, the expected cost of flooding is computed as the integral over all storm surge heights, where you multiply the probability of a given surge height times the damage that that flood depth would cause. And this expected value is equal to the fair price of flood insurance. Now, CM does not compute sea level rise within the model. I take an exogenous input scenario going out to 2200 as the input for sea level rise. And I base this work on the recent results of the Risky Business Project, which provide full probability distributions for 3 different climate scenarios. And these distributions are based on a combination of process and climate models and expert opinion. And so each time I run CM, I take one of these sea level rise pathways from the distribution and use that as the amount of sea level rise that will be faced by the model. And this figure gives you an idea of the range that I'm covering. So the bold lines are their median projections, and then I show from the 5th to the 95th percentile. So I use CM to investigate 4 benchmark policies that I've listed here from most to least restrictive. So in the no adaptation policy, I assume that all segments just do nothing in advance of sea level rise. They just react to it as it happens. In the full protect and full retreat policies, I force all coastal segments to either protect or retreat. And these first 3 are not meant to be realistic scenarios, but they're very useful in putting a bound on the potential costs. And finally, I allow each coastal segment to choose its own least cost adaptation strategy. Now, I also consider many sensitivity cases that I've listed here, looking at parameters like the discount rate and different adaptation cost coefficients. I don't have time to show these results unless people are interested in the Q&A, but I've bolded the most sensitive dimension down here at the bottom, which assumes very pessimistic case for coastal adaptation costs on both options. But even here, we're only talking about increasing the total net cost by less than a factor of 2. So this is the model setup. Now I'll present some results. This figure shows the net present value of coastal damages going out to 2200 for each of the 4 policies that I described for the 3 different sea level rise scenarios. Now, the colored blocks indicate different cost types with adaptation costs at the bottom and then residual damage costs on top. And the main results are the median sea level rise projection, and the error bar shows the range from the 5th to the 95th percentile. So starting off on the left, looking at this no adaptation policy, we can see that retreat is going to be very costly because it has not been planned in advance. And then there's a large cost that comes from inundation. And more so than the inundated land, most of this cost is actually the inundated capital that hasn't been efficiently depreciated. And another large component of these costs is the expected flood cost. And this is because sea level rise is going to have an additive effect on storm surge levels. So if we're not keeping pace with adaptation, then we're putting more people and capital at risk in the floodplain. And you can see that within each sea level rise scenario, the costs do increase. But what's more striking as you look across the diagram is that much more so than the actual sea level rise, it's the type of adaptation policy that has the largest effect in determining the overall magnitude of the cost. And this suggests that how we adapt is a much more important factor than what the particular sea level rise threat that we face will be. Now, looking at the 2 middle cases, if we could only retreat or only protect, we see that protection is a much more costly adaptation strategy. And this is not just due to the cost of building and maintaining seawalls, but because of this major effect to wetlands that I described earlier. And finally, if we let each segment choose its least cost adaptation, we can see that there's a huge potential for adaptation to reduce the expected cost in the coastal sector by more than a factor of 5. And this is because the decisions are being driven by these local characteristics. And one way to get a sense of these local characteristics is by looking at this map of coastal adaptation decisions. And here, the blue dots indicate the choice to protect, and the red crosses are the choice, sorry, the blue dots indicate retreat, and the red crosses are to protect. And the shade of the color indicates the extent of the adaptation. Now, looking at a result like this gives you a sense, if all of the previous studies were only computing coastal impacts at the country level or even the regional level, this increases the resolution by over 2 orders of magnitude. And so one of the strengths of CM is that it has this global scope, but is still able to look at local adaptation decisions. So looking at the chart, you can see that it's mostly blue. So there's widespread retreat. And so protection is pursued much more selectively. So in the entire model, only 1,000 segments choose to protect. And this is because of what I showed earlier, that protection is just a more expensive adaptation option. The exception to this rule is for areas that we know to be low-lying and to have high density of people and capital assets, in which case the cost of relocating them would be more expensive. Now, there are some really important special cases like the Maldives and Bangladesh and even Miami, Florida, that I don't have time to get into now, but we can talk about them in the Q&A. But it is important to think about these, and I just want to kind of set that up in case we want to talk about it later. But I'm going to keep going to make sure that I get through the full story. Now, because before I showed you the net present value of costs, which you kind of lose the dimension of time. And so here I'm just showing for the high emissions case, the no adaptation policy contrasted to the least cost case. And one point to make here is that the costs don't continue to increase indefinitely over time. This is even in an absolute measure, like trillions of dollars. And there's a few reasons for this. The main driver is the fact that for increasing amounts of sea level rise, there's just less land to be inundated. So you can think of this as coastal slopes tend to get steeper inland. A secondary factor is the fact that some of these cost types are going to naturally saturate over time. So, for example, there's only a finite amount of wetlands. And once we lose all of these, although we will continue to experience that loss in time, it's not going to continue to grow at the same pace. And finally, it's worth pointing out that although, yes, these are $1 to $3 trillion, when you put that in the context of the global GDP at that point, this is less than 0.5% of global GDP. And even when I look at a particular country and compare the costs that are incurred within that country, it's never more than 1% of GDP. Now, those same total annual adaptation costs can also be expressed as damage functions of sea level rise. So now we have sea level rise along the x-axis, and on the y-axis, the cost is expressed as a fraction of GDP. And so for each of the 4 adaptation policies, the markers indicate the actual CM results, and the lines are damage function curves that I fit to those results. And so the damage function that I've highlighted for you at the bottom is the least cost adaptation policy. And so these damage functions offer a compact way to summarize the rich underlying detail of the CM model in a compact equation that can then be used in any integrated assessment model. So you can apply these results in order to ask broader questions related to the optimal amount of mitigation. So as I showed up front, the current state of coastal damage functions has a huge range, from assuming 6% of GDP down to nothing. And these damages, we accept them. They go into the US social cost of carbon estimate that's being used for policy today. So this current state of coastal damage functions motivated me to develop the CM model. And so I do this by looking at adaptation costs and residual damages starting at the local level. and I'm able to improve the spatial resolution of previous studies by over 2 orders of magnitude. And I'm also able to account for other important local effects, like flooding from storm surge, wetland loss, and relative sea level rise. And this is a new approach to quantifying coastal impacts. And so the sea and damage functions that I just showed you can help narrow the range of that previous work. And importantly, they can then also easily be used in other applications, which is something that I'll demonstrate for you in the next paper. So I've already talked a bit about some of the limitations that go along with using damage functions. Now, these deficiencies are compounded by the fact that most integrated assessment models are deterministic, and many optimize with perfect foresight. So in other words, they assume that we have perfect certainty about the future. Now, the climate system, on the other hand, is characterized by uncertainty and randomness. So in other words, it's stochastic. Previously, when integrated assessment models have tried to account for this uncertainty, they've done so with limited approaches that perform uncertainty propagation. And this includes things like sensitivity analysis or Monte Carlo simulation. And while they acknowledge that there's some uncertainty around key parameters, they're not helpful for decision making because at the end you're left with a range of possible outcomes without knowing which one might be best. And so a more realistic alternative is to incorporate this uncertainty in the model structure itself in a decision theoretic framework. Now, sequential decision making is a type of model where learning happens over time. And these are called act first, then learn, because uncertainty will be resolved, but we have to make decisions before that happens. So they look for a single strategy that performs reasonably well, given the range of possible outcomes. And this one strategy is called the hedging strategy. Now, one special type of uncertainty within the climate system is the potential for a climate catastrophe. So this is a low probability but high consequence event. Act then learn is very well suited for this type of problem because we want an insurance policy against that catastrophic outcome. And so the hedging path will tell us how big that insurance policy ought to be. So to recap, one limitation of damage functions is that they haven't done a good job of accounting for damage uncertainty, specifically about catastrophes. And so we might be worried that they underestimate the optimal mitigation policy. Now, it's not a trivial task to apply these stochastic optimization techniques to integrated assessment models, which to begin with are nonlinear, dynamic, and they have multiple dimensions. But with computing advances, combined with an improved scientific understanding about catastrophes, we're able to apply these more sophisticated computational approaches like stochastic and dynamic programming in order to think about these issues. And so what I've done in this paper is to do just that in order to look at the possible collapse of the West Antarctic ice sheet. So the West Antarctic ice sheet, or WAIS, made big news a few months ago because of 2 studies, independent studies that came out on the same day, and they each suggest that the ice sheet has gone from a state of being stable to unstable. And the scientists don't know when this might happen, but they think that a collapse is very likely at some point in the future. So here's a map of Antarctica, and there's a mountain range that runs right along here, separating the west from the east side. Now the East Antarctic ice sheet stores over 53 meters of sea level rise, but it's relatively stable and may actually get bigger with climate change due to snowfall that would accumulate on top. What we're worried about is this slide, WAIS. WAIS stores about 5 meters of sea level rise, but it's particularly vulnerable because it's a marine ice sheet, which means that its base is below sea level. And as warming ocean temperatures are beginning to cause melting from underneath of the ice sheet, of the ice shelves that are the structural supports of the ice sheet, this is compounded by the fact that WAIS has what's known as a dynamic instability. So this means that as you move inland, the bedrock actually slopes down. And so there's more and more heavy ice piling up, pushing down, and it's more likely to trigger a collapse. Now, when I say collapse, this sounds like a very sudden event. When in reality, this is also a process that will unfold over time. So the scientists think that it might take 1,000 years for WAIS to disintegrate, If it were to happen quickly, it could be as fast as 200. So when I say collapse, I'm going to be referring to the start of this process that will unfold over time, and I look at a range of possible lifetimes. Now, my study models the risk of waste collapse with endogenous uncertainty. And endogenous uncertainty means that the uncertain parameters are computed within the model itself as variables. This is an important twist on classic stochastic programming, where the probabilities are instead specified at the outset, exogenously. The one final characteristic of climate catastrophes is that the likelihood of a future catastrophe is not some fixed probability that we know today, but rather that it would increase with warming. And so in the context of an integrated assessment model, this means that that probability is a function of the model itself, particularly the climate variables. And one that we can look at is temperature, which itself is controlled by how much mitigation we choose to do. Now, what I'm describing has recently been applied to an integrated assessment model by Tom Rutherford. And this has been accompanied by a surge in some recent work looking at the same type of endogenous hazard. Now, while the contributions of these 4 papers has been very notable from a methodological perspective, they each make arbitrary assumptions in characterizing the catastrophe that they look at. So, for example, the catastrophe means that you lose 10% of your GDP going forward. Now, these arbitrary assumptions are fine for a demonstration, but it's not something that we're going to base policy on. So I'm going to build from here in order to progress beyond the generic stylized catastrophe with arbitrary assumptions. Because the goal is to inform policy and be of aid to decision makers, that it's important that we think about how the catastrophe might be characterized in an accurate way. And so I start with the definition of risk being equal to the probability times the consequence. And each of these 2 terms, the hazard and the consequence, needs to be well characterized for the particular catastrophe that we're looking at. And so in the case of the waste collapse, I base that characterization on physical relationships between the climate system and the temperature of the local Antarctic Ocean warming, empirical results about the rate of ice sheet disintegration, and expert elicitation about the likelihood of this collapse. And these are a few sources that I've used for this calibration. Now, I think it's helpful to see the stochastic program as a scenario tree. And the model runs in 10-year time steps. So starting out, the ice sheet can collapse with probability HR or not. And going forward, the collapse can happen in any future time period if it hasn't already happened. And in that time period, the likelihood is given by the updated hazard rate, HR sub t. And so the important design feature here is that these HR sub t's are not specified at the outset, but instead they're evolving along with the model, and it is linked to the amount of warming. So the more climate change that happens, the more likely this collapse. And specifically, I calibrate the hazard rate to this recent science that I listed on the previous slide. And this is consistent with the understanding that it's the temperature of the local Antarctic Ocean that is going to trigger the collapse. And the fact that this term is squared means that small amounts of increase in ocean warming are going to have an amplified effect in increasing the probability. So I integrate that scenario tree with an integrated assessment model. And the model that I use is the DICE model. So if you're not already familiar with it, DICE is a very simple global model of economic growth. And the objective is to maximize net welfare of society over time. Now, global production, or output, has the consequence of CO2 emissions, which alters the climate system and causes climate damages, or omega T. And these are claimed from the current year's GDP. Now, there is a way to slow climate change by investing in mitigation to decarbonize the economy. And this variable mu tells you the fraction of annual emissions that have been controlled. And I limit how quickly it can increase over time in order to reflect technology inertia. Now, I modify the DICE model in order to include a sea level rise component. And so here we have warming from climate change that also drives baseline sea level rise from thermal expansion and from ice melt, but not from waste. And sea level rise also has a cost to society, and this is represented in omega S. Now to begin with, I'm going to be using the dice damage function for omega s. And this is the quadratic damage function that I showed you earlier. But later, I'm going to use the CM damage functions as an alternate case. Now, if the waste collapse has occurred, this triggers an additional source of sea level rise, and this increases damages in the coastal sector. So when I run the model, these are the sea level rise outcomes that correspond to the collapse case branches on that scenario tree. And here we have sea level rise in meters on the y-axis. And this gray line at the bottom shows the baseline sea level rise that would occur if the waste does not collapse. And then each of the red lines peeling off in turn reflect a collapse in a given year. And you can see that the sooner the collapse happens, the more sea level rise society is going to have to deal with this century. So the question is, does this new threat change the optimal mitigation solution? And in short, it does. So here the y-axis is the mitigation level, the fraction of emissions that have been controlled. And just having the threat of collapse causes the model to do more mitigation. And so we see this in the increase from the gray mitigation line, which is how much we would mitigate if we were ignorant about the waste collapse, up to the black line, which is if the collapse has not yet happened, but the threat is still out there. And then each of these red lines show that if the collapse does occur, then doing more mitigation is even more valuable. And this is because of the additional source of sea level rise moves you to a steeper slope on the quadratic sea level rise damage function. Now from a policy perspective, what we're interested here is in the black line, which is the pre-collapse level of mitigation. Because if we were going to set a policy, that's where we would want to set it in order to avoid or at least delay the collapse. So we find that the policy recommends more mitigation. Now, why would we see that? The additional mitigation can be decomposed into two different components. The first is the hedging motive. So by doing more mitigation early, this serves as a hedge against ending up in one of the collapse states of the world. The second is what I call the precautionary motive. So you can do more mitigation in order to reduce those probabilities and make it less likely that the collapse happens. Now these two factors can be shown analytically to be additively separable. So I do one final experiment. I've been running the model in endogenous mode, where both of these two motives are present. But in contrast, in a classic stochastic program with exogenous probabilities, there's no option for precaution. And so by comparing these two modes, I can separate and identify the different contributions of the two factors. So I run the model as before, and in each time period, I observed what the hazard rate turned out to be. And then I save those probabilities off to the side. Then I run the model again, but this time I supply those probabilities to the stochastic program exogenously. So now I've removed the second reason for mitigation, and this is going to allow me to identify the precautionary motive. So here, what we see is that the blue line only reflects the hedging motive. And so specifically, I find that of these two factors for mitigation, it's the precautionary motive that explains most of the optimal response. And so the message here is that it's not just enough to do stochastic programming. If we don't account for the endogenous nature of catastrophes, then we may underestimate how much mitigation we should do. So all of these results have been using the dice damage function, because that was available to me and I was using the dice model. But in parallel, I was developing CM. So I had always planned to rerun the analysis using the CM damage function, because I think that there's a good reason to believe that they're more credible. But for where DICE projects 6% of GDP loss, CM suggests that it may be more like 0.5% of GDP loss. And importantly, the slope of CM's damage function is linear, not quadratic. And so you can see that the entire effect that I've been describing to you with the hedging and the precautionary motive goes away. And even baseline sea level rise warrants much less mitigation. And strikingly, the potential collapse of waste has very, almost an indistinguishable effect on the mitigation policy. And so this would suggest that the waste collapse is not nearly as catastrophic as some would suggest. So based on my dissertation research, I find that sea level rise and the potential for sea level rise related catastrophes, like the collapse of these ice sheets, might not be a strong driver of mitigation policy. And I didn't know this at the outset. It took me going through these two projects to come to this conclusion. Now, this isn't to say that we don't need strong mitigation policy. It's more that sea level rise is not going to be the driving basis for that mitigation policy. Now, there are other really important climate impacts and climate catastrophes that are going to require strong mitigation and precautionary mitigation. And so I think a really important lesson here is that we need to be able to do the same type of analysis to look at other climate impacts and other climate catastrophes so that we can design policy, find the right policy that would accommodate those. So to conclude this paper, previous integrated assessment modeling studies either did not account for the uncertainty in the climate system or tended to do so in a limited fashion without incorporating it into the model structure itself. And these new stochastic optimization techniques allow us to do this. And my contribution to the work that's recently been done is to emphasize that these catastrophes need to be very well characterized if they're going to be useful for policymakers and to provide policy insight. And this is not just characterizing the physical consequences, but also the social or the economic consequences. And this comes down to the damage functions and making sure that those are credible. And simply by substituting my CM damage functions in for the DICE damage functions without changing anything else in the model, you can see that that has the potential for drastically changing the policy conclusion. Now, I've looked at waste. It would be nice if this was the only climate catastrophe that's out there, but it's not, and I think that the same analysis should be done for other catastrophes that we're worried about, such as the collapse of the thermohaline ocean circulation, the rapid release of methane from hydrates in the ocean or from permafrost, or forest dieback, just to name a few. The important thing is that each of these catastrophes I've listed, each have their own distinct characteristics that need to be accounted for within the model calibration. And importantly, we need to move in the direction that dealing with one catastrophe at a time is not enough. In the real world, we face multiple threats. And so we need to evolve to have models that are able to account for these multiple catastrophes. Now, overall in my dissertation, I find that damage functions and the way that they've been used in integrated assessment models have serious limitations and require some attention. So in my first paper, I find a lot of evidence that the damage functions that are in use today are very out of date. They only reflect a fraction of the science of impacts, adaptation, and vulnerability, and they lack a really strong empirical basis. And so one case that I've shown is for damage functions of sea level rise. And the work that I've presented with the CM model is one way to provide credibility and rigor to these damage functions. And then by using the endogenous hazard model, I demonstrate a way that precautionary policy could help manage the risks of climate change. So I think that both of these approaches of the second and third paper could be applied to other climate impacts and other climate catastrophes. One conclusion from my dissertation research is that sea level rise is not likely to be as costly as it has been portrayed in the media. What I find is that sea level rise impacts are going to entail adaptation costs, and there will be transitions that we have to go through. And there are going to be serious distributional impacts related to small island states, and we're going to need to find solutions for these situations. But looking on the global level, overall the costs are likely to be small, less than 1% of GDP. I think this fascination with sea level rise is because images like this can capture people's imagination. But there's a real danger in using sea level rise in a sensational or alarmist fashion, because sea level rise, from my work, suggests that it's not likely to be as costly as other climate impacts. And I think importantly, it could actually serve as a distraction from spending the time to look into the other climate impacts and climate catastrophes that would warrant more stringent policy. So this is definitely not a reason for inaction on climate change, but rather a call to action to study other climate impacts in more detail so that we can design the right policy. Now, my last slide takes a step back from my dissertation. And so if you think of managing climate change as balancing the costs of mitigation with the benefits of avoiding climate change, my dissertation has been looking at those benefits, and specifically how they're represented in damage functions. But I see my future as a researcher as working on both sides of the cost-benefit ledger. And before I came to Stanford, the work that I did at EPRI was more focused around understanding the cost of mitigation and the role that would be played by different energy technologies. And a lot of my work when I started in the program was along this same vein. And so I was looking at these same integrated assessment models, but instead looking at how the energy technology representation accounts for technology change, and also how the energy system might respond to different carbon prices. Going forward, I'd like to continue to work on damage functions and strengthening their empirical basis. And so I've kind of coined this IAM-IAV gap, which is a disconnect between the integrated assessment modeling community and the scientists who study impacts, adaptation, and vulnerability. And so this gap has developed over 20 years, when ideally these two communities should be working side by side in order to make sure that the latest climate impact research is making its way into the integrated assessment models. I think the gap can be explained by factors that are related to funding and research collaborations, but I think that this is a really important area that I'd like to spend some time in. And one initial step into the area has been work with Fran Moore, looking at a new type of damage function. So rather than have climate damages affect GDP output, there's recent empirical evidence to suggest that it might have a more persistent effect on GDP growth rates. And so we test this in an integrated assessment model and find that it has substantial effects, increasing the social cost of carbon. And so I think that these new types of damage functions are really worthy of future research, and so I'd like to spend some time there. And finally, I'd like to see integrated assessment models used less for deterministic analyses and more in ways that are useful in terms of managing the risks of climate change. So I've demonstrated an approach for one particular catastrophe, but I think that this type of study is useful for decision makers so that they can begin to understand this idea of insurance policies that balance the costs of mitigation today with the future downside risks of climate change.
Some time for questions from the audience.
This is the first.
This is not okay.
It's too late now.
What makes Miami so special?
That was I set that up.
Too many Cubans.
So if you look at the results of the CM model, Miami is seen as a place where we would want to build protection. And from the modeling perspective, this is because Miami is very low-lying and there's a high density of people and capital, so it would be costly to retreat. And so if you look at Miami, Florida, it's covered in these red X's. And that makes sense if you think it through based on how the model is making the decision. But there are these special cases that CM has not, at least in its current state, has not accounted for every special case that's out there. So we know that Miami is not a good candidate for building protection because of the porous limestone foundation. And so even if you build a seawall, the sea level is, the rising seas will just bubble up from underneath. There could be ways to account for this so some special cases could be treated in designing the parameters. So rather than assume this kind of generalized seawall, I could adjust the protection costs for Southwest Florida to make it more expensive to reflect the fact that protection is not going to be as cost effective in that location. But so it's this idea that CM is treating over 12,000 segments following the exact same procedure for each of them. And it's designed for the general case, not dealing with these special cases. I think there's a really important role that is going to continue to be played by local studies. I think that John alluded to this in his introduction. Local studies that will have their own very specialized assessments. So CM is certainly not going to replace those, but I think that while those specialized studies can't then be extrapolated to understand global costs, this might not get every segment right, but it's going to get, on the whole, it's providing a more comprehensive estimate of costs.
Thank you.
Okay, over here.
Great presentation. I was wondering if you could talk a little bit about the optimal adaptation assumption, and if, in reality it's not optimal, when people wait 10 or 20 years and sustain a few floods and really then retreat gradually versus immediately. How does that shape the damage estimates, and how does it also affect where your mitigation policy would fall?
Yeah, that's a great question. So in terms of the adaptation costs, and I think that's probably a likely scenario, that it's going to take a few big floods for us to kind of really believe the threat that's coming down the pipeline and invest in these adaptation options. I don't do any cases where I assume no adaptation for 20 years and then have adaptation options kind of kick in as before. I think that that's certainly something that would be easy to do within the model structure. The result that you would see is that for the first few decision periods, it would look like the no adaptation policy, where we were experiencing a lot of capital loss in those first few periods, both due to flooding, but also maybe some inundation that happened. And so I can at least put a bound that that's going to be less than 1% of GDP. And maybe that's the wake-up call that we need. In terms of changing the damage functions, it would kind of create some non-convexity where costs were high and then came down and then continued along the slope that I showed before. That might present its own problems for using in an optimization model, just due to kind of the computational nature. But I think that knowing that what I'm showing is kind of assuming at 4 meters of sea level rise about 0.5% of GDP, even if you looked at something that was 2, 3, 4, even 5 times the magnitude, the fact from designing mitigation policy, without getting too much into the math, it's actually the slopes of the damage functions that play a really big role. And so sea level rise is probably going to have no greater than a linear slope in terms of how damages accumulate over time. And so they're not as responsive in terms of mitigation. And this one feature is going to mean that there's just, simply because of the derivatives, there's going to be less mitigation that is driven by sea level rise.
Okay, yeah, over there.
Yeah, so I'm guessing a big part of why this picture is mostly blue is that maybe those areas are not populated, right? So do you know if people are moving towards the coast or away from the coast? And can we easily add this, probabilities into the model to see how this changes?
Yeah, that's a great question. So coastal population growth happens more quickly than kind of a national average. And this is being accounted for within the model based on kind of the initial data set, what current coastal population growth rates, what the current coastal population density is. So one thing that was on a slide I didn't mention explicitly, I am assuming the country level population growth. So to the extent that coastal segments are going to have faster population growth, that would increase the future damages simply because with more people there will also be more capital assets. This idea that coasts, it's not clear whether coasts are going to continue to be have the same amenity value of where they are today. They're always going to be great from kind of an economic perspective in terms of having access to transportation and shipping routes. But yeah, I wouldn't think that having faster population growth within the coastal segments would drastically change the results. That would be another sensitivity case that I could look at.
Any more? Yeah, how about over there?
I was wondering, so one of the things that seems so interesting here is that you can get such fine-grained assessments of the impact of sea level rise. So have you seen in integrated assessment models or in policy discussions, or what role could that play in understanding the distributional impacts and the viability of implementing various policies, given that if we're looking at global response to climate change, those distributional impacts become really important. So does the existing discussion break down damages at this level, or could your model contribute to those discussions by breaking down?
Yeah, I think that with the exception of some special cases like countries that we know are going to disproportionately feel the impacts of climate change, whether that's Africa or, in the case of sea level rise, Bangladesh. Most of the conversation has not been at the level of granularity that I'm tracking in this model. I don't know that that needs to happen. I think that looking broadly, within the last few months, there's been a lot more discussion about how poor countries are really going to kind of need to have assistance along this process of adaptation. And there's people in the room that I think have spent a lot of time, kind of helping get that message out in terms of where impacts are going to be felt most strongly. I don't know that this type of decomposition of adaptation costs necessarily has a place to weigh in on that specific conversation. I think it's useful in providing some credibility and at least kind of understanding where the adaptation costs are likely to be bigger than others. But I think that I would be cautious in kind of putting them into the same that same conversation.
Okay, I think we need to wrap up the questions.
Okay.
Do you have any final remarks?
Yeah, I do. I have. I have an account. Thank you, Sally. Well, so I want to start by thanking my committee. Sally, it means a lot that you were able to serve as the chair. Our first interaction was before I came to Stanford. You came to speak at the EPRI Technical Women's Network retreat. And even since then, you've been someone in the energy community that I just have a lot of respect for, both for your technical expertise, but also your leadership. And I've enjoyed taking classes and attending the energy seminar since being at Stanford, so thanks for serving as chair. John and Jim, I feel so lucky to be in the Energy and Environment program of MS&E, and it was so great working with both of you during my first 2 years on my tutorial papers. John, you continue to amaze me with your ability to kind of put this research into the broader context, whether it's the integrated assessment modeling community or kind of always seeing the broader policy context. I feel like whenever I come to you with one very specific question during one of our weekly meetings, I leave with kind of a much wider appreciation of where this fits into the whole research community. I have a list of names of people to look up, and I've heard a few stories along the way. So it's always been fun. Thank you for being my advisor from the day I arrived at Stanford, and you've given me so much support, both personally and professionally. Jim, I've really enjoyed working with you. I know that you're always going to ask questions that get right at the heart of the matter. I also really appreciate how willingly and often you get up from your desk in order to work something out with me on the whiteboard side by side. That means a lot. Chris, I just want to thank you for saying yes to being on my reading committee. Not like you didn't have a busy year ahead of you with the IPCC. But I really value your perspective, and the thoughtful comments and feedback that you provided along the way have been very helpful. And Gerd, you've been so generous in giving me time over the past year. I couldn't ask for a more enthusiastic reader, so thank you. It's been a pleasure to work with you. I want to acknowledge some generous funding that I've had these past 5 years. Starting out at Stanford with the SGF was such a great experience. In my first year, I was able to take classes from 10 different departments, and that really allowed me to see the breadth of Stanford. And since then, I've been supported by a Department of Energy grant for integrated assessment research, and also partial support from EPRI for the Social Cost of Carbon project. I want to say a big thanks to all of the staff that keep these programs running, Lori and Juanita in MS&E Student Services, Pam and Anna for helping us keep track of where John and Jim are, and of course Catherine, who we all miss, and is back in Ohio. So a lot of you out here I'm lumping into what we now affectionately call the energy box, which is our studio.
Sounds like a torture.
And this, it includes everyone, even if you left before the energy box was constructed over winter quarter. But I just want to thank you guys for so many fascinating discussions and great distractions from work. And we've had a lot of good extracurriculars along the way, like hiking in the Berkeley Hills or doing brewery tours. It's been a lot of fun, and you guys have made the program what it is. And of course, there's also this wider interdisciplinary collection of peers that I've had the opportunity to work with. And I think the PER and the CPAC seminars are a great way for connecting with this community, and also have been a really good opportunity for me to present early work along the way and get feedback. I want to acknowledge the Hume Center here at Stanford. I've already done a couple of these dissertation boot camps, and they've been great. And I've also had the opportunity to work with tutors. And similarly, the technical writing program within the School of Engineering has been really useful, and I recommend to other people to take advantage of. I have to acknowledge Adam Grant, who's not here. His class that I took in my first year at Stanford on energy optimization is probably the single best class that I've taken, and I continue to use this on a daily basis. So I really have to thank him for giving me the skills that I've been able to use over the next 4 years. And I want to thank my EPRI colleagues for just being great to bounce ideas off with, and it's been wonderful to collaborate with them along the way. And finally, there's so many faces here from the broader Palo Alto community. I knew most of you guys well before I started at Stanford, and it's really nice to have had your support along the way. Many of you, we've been playing volleyball here for the last 7 years, and that's been a great part of my life here in Palo Alto. And of course, I want to thank my family, who fortunately made it through the storms yesterday. You wouldn't think that you'd have to leave Tampa, Florida to encounter hurricane forces. But everyone made it.
They brought it with them.
If anything, maybe worrying about them was a nice distraction from being nervous here today. And of course, I couldn't have done this without Jack, who's been cheering me along from the very beginning. From literally six years ago, when I told him I was going to cancel our Thanksgiving plans because I wanted to study for the GRE and submit an application.